Today we're going to look at Lagrange multipliers as a way to optimize a function subject to a constraint. So the Lagrange multiplier is for optimizing a function f subject to constraints we want to optimize a function f subject to some constraint. The function that we're trying to optimize, that's going to be our objective function. And the other one is going to be the constraint function. So the function g has to be some fixed value, whereas the function f is the one that we're trying to optimize. So we might be trying to optimize the volume of a box subject to some constraint that's represented by the amount of material that we're limited to use. At that point, I guess we have to specify the shape that we want the box to be, but maximize the volume subject to some constraint. Or maybe we just have to have optimize the amount of material that we use to contain a particular volume. So how much volume can we enclose with 100 square feet of material? Or what is the least amount of material that we need to enclose 5 cubic meters? That seems like a lot. I don't know why I had to go so big. I guess it's because it's Friday. So we know what we're supposed to do. We want to set the first derivatives equal to 0 and solve, but then we just have this extra requirement that g is equal to k. So what we want to do is we want to solve this system where the gradient of f is equal to lambda times the gradient of g, and g is equal to k. So when we write the gradient of f equals lambda times the gradient of g, this means things mechanically with the first derivatives, but it also means things geometrically because these are vectors. So if the gradient of f is just lambda, a scalar, times the gradient of g, that is telling us that the gradient of f and the gradient of g are pointing in the same direction. So that's geometrically why we care about gradient of f equal lambda times gradient of g. So this is telling us that gradient of f and the gradient of g have the same direction. We're looking for a point where the gradient of f and the gradient of g are pointed in the same direction. So we're looking for a point where the objective function is tangent to the constraint. So if gradient of f and gradient of g are pointed in the same direction, gradient of f is perpendicular to the contour, gradient of g perpendicular to the contour. So I'm looking for the contours to be parallel. Contours are tangent to each other. So that's the point that we're looking for. The g equals k part, make sure that we have the right contour of g. That's telling us to use a particular contour of g. So G equals K is one of the level curves. And I'm looking for the level curve of F that's going to be tangent to this particular contour of G. I want the gradients to point in the same direction. What this means mechanically is that x I hat plus fy j hat is equal to lambda times gx I hat plus gy j hat. So we want fx to equal lambda times gx and fy to equal lambda times gy. That's what we're asking. We know that optimizing functions is about setting first derivatives equal to 0. So what we're looking for is where fx minus lambda times gx is equal to 0. That's another way to frame what's going on here. So I might also read this as fx minus lambda gx equals 0, and fy minus lambda gy is equal to 0. Notice that the zeros over here are scalar zeros. When I wanted the gradient of f to equal 0, that was a vector 0. But these are scalar zeros. So there's our first derivatives combined together, set equal to 0. So let's still take the first derivative, set equals 0 and solve. This is just us including the constraint information. Any questions? All right. So let's do an example problem. I'm going to choose this particular textbook's favorite example. I think it's production function. Is that what it's called? I had to look it up. Yep, Cobb-Douglas production function. So the Cobb-Douglas production function says that our total production is a function of capital and labor. The order, something like that. Our total production is a function of capital and labor. So L is just going to be in labor units, person years, hours that need to be done, presumably by humans or our future robot overlords. So capital will be our equipment, our machinery, stuff we got about building, maybe. The labor, so it's our production, our total production is a function of capital and labor. When this is set up, It's written as the product of k to some power alpha and L to the 1 minus alpha for reasons. To explain why total production is going to be this product, it's easy to see why total production will be a product of capital and labor. You buy some stuff, you hire some people, you start producing. But the reason that it's k to the alpha times L to the 1 minus alpha, that you're going to have to ask Cobb and Douglas. That's a business question. This is a math class. I don't care. I just see a cool function where the exponents add up to 1. So apparently there's some kind of thinking these exponents need to add up to 1. So if k is raised to the 0.4, L will be raised to the 0.6. I think if I had read further, there might have been an explanation. There's like a whole Wikipedia page, but I'm like, oh, that's okay. I got my function. I'm ready to go. And for years and years and years, I've never looked it up. And no one's ever asked me about it because it's just a function. This is a math class. We're just using all this stuff. Now, this would be subject to some constraints. We can't just have total production be the product of capital and labor. Then we'll have just infinite production with infinite labor and infinite capital. Or if one is fixed, make the other infinite, and we'll have infinite production. So clearly, there's some kind of restriction. We'll have some budget, and this will restrict how many labor units we can purchase and how much capital we can purchase. Our budget is much more straightforward. We want to spend, each unit of capital costs a certain amount. Each unit of labor will cost a certain amount. So our budget should be our number of capital units by the unit cost per capital unit. That's what M is going to represent. And N will be the unit cost per labor unit. And this will be some fixed budget. So we have a Lagrange Multipliers problem. We want to optimize, probably maximize our production subject to a given budget. I'm not quite sure why the exponents have to add up to 1. Because like I said, I didn't read further when I first looked this up. Because I got my function and that's all I really wanted. Presumably there's some other stuff in the total production. It's not just going to be a coefficient of 1. So there might be some other coefficients. So that beta will be some other coefficient that gets multiplied in to the total production. We make our calculation of labor and capital, raised to the appropriate exponents, then we multiply by some coefficient. Just like with gravity. Gravity is the product of the masses divided by the square of the distance between them, multiplied by some constant, gravity, the gravitational constant, presumably the gravitational constant of the universe. A quantity whose value and units escape me at the moment, because all I need to know is it's a big G. And I can leave the explaining of that to physics. Any questions? How's everybody okay? High pressure business school, which you all wore in suits and ties. All right. Let's do an example. Let's suppose that we want to maximize P of K and L, which is going to be K to the, how did I split it up? 2/3 and 1/3. So I have, excuse me. I want to maximize my production, and it's subject to this constraint. Apparently, each capital unit costs 10, and each labor unit only costs 4. So I could spend my 60 unit budget on 6 units of capital, but then I would have 0 labor, and my total production will be 0. Well, that's no good. I could swing it the other way. I could take 15 units of labor. That would be my whole 60 unit budget. But then I would have 0 to spend on capital. So that would give me 0 total production. I hire all these people and don't have any machines for them to work on. Or I have a bunch of machines, I don't have any people to work on the machine. I suppose if we have robots that work the machines, they're going to have to be counted as people for the purposes of this labor calculation. So we're going to have some mix of K and L to get our production off the ground. And we want to know what the optimum distribution of K and L is going to be. Any questions? Let's proceed. We want the gradient of P to equal lambda times the gradient of B. And we also want B to equal 60. So this is the system of equations that we're going to solve. This requires our first partials. So I need PK. The derivative with respect to K will be 2/3, K to the negative 1/3, L to the 1/3. And PL will be 1/3, K to the 2/3, L to the negative 1/3. Now I just have opposite exponents. L to the negative 2/3. So we end up with these opposite exponents. I wonder if that's why they wanted it to add up to 1. So we just get this cool situation. I also need lambda times the gradient of B. So I need lambda times BK. The derivative of BK, B of K, B with respect to K is just going to be 10. I still have the lambda, my Lagrange multiplier. I also need lambda times BL. So over on this side, I got the components of gradient of P. Over on this side, I got the components of lambda times the gradient of B. I want these to go in the same direction, so I'm going to set them equal to each other. And so we have this weird system, 2/3, k to the negative 1/3, L to the 1/3 equals 10 lambda, and 1/3, k to the 2/3, L to the negative 2/3 is equal to 4 lambda. I use my three equations to put together my three unknowns, A, L, and lambda. Now we come to the part which is the other reason I chose this problem. Our constraint function is a linear function, and so I can solve for lambda in both of these. So I can take this first one and say that lambda is, let's see, divide by 10, so 1/15 k to the negative 1/3, L to the 1/3. I'll solve for lambda in the second equation to get 1/12 k to the 2/3, L to the negative 2/3. So what, excuse me, so what we're doing is solving for lambda in one equation and plugging it into the other equation. The same thing we always do when we're trying to solve systems. Solve one of the equations for one of the variables, plug it into the other equation. So this gives us 1/15 k to the negative 1/3, L to the 1/3 is equal to 1/12 k to the 2/3, L to the negative 2/3. And this is where I became super suspicious that these add up to 1, so this exact thing would happen. Now I can multiply to solve for L or K. I'm going to multiply by 15 k to the 1/3, L to the 2/3. So I'm going to take this equation from lambda equals lambda, and I want to multiply it by 15 k to the 1/3, L to the 2/3. Is the equation so simple to make because that's how things actually are, or is it just so that this would happen when we multiply? The 1/15 times the 15 cancels out. K to the 1/3 times k to the negative 1/3 cancels out. L to the 1/3 times L to the 2/3 is L to the 1. (1/12) times 15 is 15/12. K to the 2/3 times k to the 1/3 is k to the 1. And L to the negative 2/3 times L to the 2/3 is 1. So L is just 15/12 k. This happens all the time in this problem. You just get some ratio of L and K. And it works out so nice because those exponents add up to 1. So when we take derivatives, they conveniently cancel out. So is the production model work out because we're lucky, or did we design it to work out this way? But once we have that L is 15/12 of K, we can plug that in to another equation. To find out L, or actually to find out K. And fortunately, we still have another equation involving K and L running around that we haven't used yet, which is our constraint. So 10K plus 4L is equal to 60. And that becomes 10K plus 4 times 15 over 12. Let's take out a 3, so 5/4. So 15K is equal to 60, and K is equal to 4. If K is equal to 4, then L is 5/4 of 4. So it seems as though in this situation, if capital and labor are related K to the 2/3 times L to the 1/3, and if capital costs 10 per unit and labor costs 4 per unit, and we've got 60 units to work with, we should purchase 4 capital units and 5 labor units. That will use up our 60 unit budget and maximize our total production. And we can even calculate what that maximum production is, whatever that happens to mean. K of 4 capital and 5 labor is going to be 4 to the 2/3 times 5 to the 1/3. For me, I don't just have to put a smiley face there. So apparently our maximum total production will be 4.31 units. Question? Well, wait, there's more, because I just solved for L and K, but there were 3 equations with 3 unknowns, 2 from the first derivatives and 1 from our constraints. So there is another value running around, and that's lambda. So lambda will represent how much production will change if our budget increases by 1 unit. Lambda will be the production increase lambda will tell us how the budget, or sorry, how production will change if we increase the budget. So if we increase to 61 units, lambda would be the approximate change in total production. It's like the slope of the production with respect to the budget. That's what the units of lambda could be. Change in, excuse me, change in production per unit of budget. Any questions? How's everybody okay? Can't wait to get to business school now. Now, this problem is not going to raise many questions because the problem isn't too difficult. Usually we only get, why do we have to know this type of questions when the work gets too difficult? So if you're doing some work in math class especially, and you start thinking, man, when am I ever going to have to do this? You should recognize that that's a sign, first of all, that you don't want to do it. And second of all, that you're actually going to have to start putting some work into it. That makes sense? You need to recognize these signs. Because if you've been through all your math classes, and at no point have you said, man, when am I ever going to have to do this? You might not have been challenged at ending your math class. Think about the times you ask yourself why you in particular have to know this. Why are we picking on you? Versus the times that you felt you were struggling in math class. Because when you're not struggling, you don't really care what the point is. It's like, oh, this is easy. And you think this class is going to be 3 points. Some of you, this class is going to be 3 points. It's just going to be an easy A for you. Some of you are going to have to work harder at it. You know what I mean? But know the signs. When you start thinking, man, I'm never going to be doing this. I'm not going to be a business person. I want to design computer chips, make big piles of money doing engineer stuff. Cobb-Douglas production function, not the point. Lagrange multipliers and how we think about optimization, that's the point. We picked this one because the numbers work out so cool. How's everybody, okay? I also picked this one because I've noticed that this gets used a lot in the blue palette book. Let's find out what their line is. Why this one so much in Lagrange multiplier? Any questions? Comments? Any thoughts? So one of our equations was 2/3 k to the negative 1/3 times L to the 1/3 is equal to 10 lambda. So we could solve for lambda as 1/15. Oh man, I had expressions for lambda. Jeez. Doing it all over again. 1/15 k to the negative 1/3 L to the 1/3. So lambda evaluated at our point 4 capital and 5 labor So our lambda is 0.028. Now this is at a budget of 60. If the budget increases to 61, we should expect the production to increase by approximately 0.028. That tells us how much increasing the budget will have, the effect the increased budget will have on our total production. So if we increase our budget from 60 to 61, we should expect total production to increase by 0.028. So 4.33. Now, this is only a linear approximation. If we actually increase the budget to 61, we should run the calculation again to figure out what lambda is. But we're treating budget as a constraint, not something else that we can optimize, that we should optimize. Although at least this lambda tells us that if we increase our budget, we will increase total production. So there's that. Any questions? Comments? Deep thoughts? How's everybody okay? All right, this seems like a lot to think about, but that's only because it's a lot to think about. One thing that you want, that I am trying to communicate, and I'll just say it explicitly so there's no miscommunication, is that I'm not really concerned with whether you understand the Cobb-Douglas production function. I'm not going to ask you to explain how that works. Everything that I would ask you to explain, everything I would ask you to do with regards to the Lagrange multiplier is going to fit into a neat little box. What can I ask you about? I can ask you to optimize. That's a mechanical problem. First derivative is equal to 0, solve. I might ask you to interpret what lambda represents. And you don't have to know anything about what's going on. I have admitted that I don't know what's going on in this problem. I don't know where that function comes from. I just stole it so I could use it as a math example, like I steal all my other examples. And it just does some interesting stuff. But that's not important because lambda is just going to be the total change in the objective function if the constraint increases by 1. If you're wondering why it's always the constraint increases by 1, is that's how we interpret slope. If the slope is 5, then y increases by 5 when x increases by 1. If the slope is 5/4, then y increases by 5/4 when x increases by 1. That's what slope represents. What happens to y when x increases by 1. None of those interpretations require that we understand what's going on. So when you're looking at a problem, you think, well, I don't understand the business applications. That's not the point. I'm not asking you to. I'm asking you to understand the mathematical computations. Any questions? Comments? Deep thoughts? How's everybody okay? There's never going to be any questions because it is Friday today. There's only like 7 minutes left in class. That's how you make people look at their watch or their clock, or sit uncomfortably not looking at the watch or the clock because I'm still looking at this. But you're looking for a reason to look at that. It's even more effective mind control if instead of on the back wall, the clock is in the center of the side wall. Because then I don't have to use my voice to do mind control. I just do this. Then everybody in the room knows that I know what time it is. You're like, oh shit, I want to know what time it is too. And so as soon as I'm not looking, I turn around, everybody goes, what time is it? You know what I mean? Mind control. We like to think that we're rational creatures, but we are hella not rational creatures. All right. Any questions? All right. That's going to do it for today. That's going to do it for this week. I'll see you all on Monday. Everybody have a good weekend, and thanks for playing.